All right, so chapter 4 talks about hormonal control during exercise. Now, one of the things that I'm trying to do in a good warm-up, number one, is I'm trying to increase heart rate. Now, if I can increase heart rate, then I'm going to distribute blood to the body. And in the blood is oxygen and fuel, right? So I'm going to get some oxygen and carbohydrate to the body. So I'll just put fuel. And also, if I can bring blood to the body or switch blood from the intestines, because when you're not exercising, a lot of the blood is in your stomach and intestines processing the food that we talked about in bioenergetics. But the blood is 98.6 degrees. So if I can get the blood out of my intestines and into my muscles, then my muscles are now going to be 98.6 degrees. And just like if you put Play-Doh in the freezer, it's not flexible. If I increase the muscle temperature to 98.6 degrees, that's going to definitely increase the flexibility of my muscles. So number one, a good warm-up is going to increase heart rate. And number two, a good warm-up is going to increase your breathing rate. Like when you run in place or when you do jumping jacks, obviously one of the results is that your breathing rate is going to increase. And when your breathing rate increases, then you're able to distribute oxygen more effectively to your muscles. Now, indirectly, one of the things that you're trying to do is, not indirectly really, is you're trying to also manipulate your hormones. So a good warm-up is going to result in some type of hormonal change or something prior to you doing exercise so that you're more prepared to do exercise. And one of the things that a good warm-up is going to do is it's going to affect your adrenal glands. And your adrenal glands, like the word adrenaline, is going to release adrenaline. And what adrenaline or epinephrine does is it increases your vasodilation. So it's going to dilate, increase the, here's DJ. It's going to increase the diameter or the thickness of the blood vessels. And it's not thickness, rather, it's more the diameter, even though I'm writing thickness right here. What it'll do is it'll make the blood vessels expand and it will make them dilate so you can get more blood through. So like thickness isn't the correct answer, but I don't want to write dilate because it'll take too long. So a good warm-up is going to manipulate your heart rate, going to manipulate your breathing rate, but it's going to do it by releasing epinephrine from your adrenal gland. And you can think of, somebody sent me a chat. Allison, no problem. All right, it's all good. Let's get rid of the chat. And you got to think of hormones, let's erase this here, as, so you have this like an aquarium, a fish tank. The fish tank is full of water. It's full of water. Now, if I take this drop of blue ink, green ink and water would be better. If I take a drop of green ink and I put it in the water, eventually what's going to happen is the ink is going to start to dissipate through the water. And eventually all of the water is going to have like a little tint of green. It's going to diffuse, it's going to disperse, it's going to kind of spread through the water. But that process doesn't happen instantaneously. It's going to take a little while for the green dot to dissolve in the water. Eventually it'll all be dissolved. But if I drop the green ink, it's going to be pretty concentrated at first. And that's kind of what happens to your hormones. Your hormones are going to be released by your glands, your adrenal glands, into your bloodstream. And it's going to take a while for that hormone to get through your entire body. It has to circulate through your vascular system. So this release of epinephrine from your adrenal gland doesn't happen instantaneously. It happens over time, which is why I want my warm-up to be about 5 to 7 minutes. Because once the epinephrine is released, it's going to take some time to travel through the bloodstream and get to each of my muscle cells and to get to the epithelial cells of your blood vessels and such. But a good warm-up is going to start to not only manipulate your body and splits and run in place, but we're going to really start to think about how we can manipulate hormones to make it so that they have more oxygen and more fuel to be better athletes. Again, if you have any questions, please let me know or just come on mic right away. This chapter talks about the endocrine system. There are a number of endocrine glands that we'll talk about, and each one of those glands releases a hormone. Here's, another thing right here, first line, chapter 4, another word, system. So it's just these little cues, little hints. What is a system? A system is anytime you have one thing connected to another. And now you have a number of things connected to another. You have the hypothalamus, the pituitary, and these things are all connected to the organs and to the tissues that they're affecting. And the thing that draws the line between the organ, between the hypothalamus and say for instance, the temperature regulation, the thing that is drawing the line between those two things is the hormone. So even in this case, a hormone is acting as a connector between the gland and whatever tissue that it's affecting. All right, the sweat glands or whatever, or so let's undo this. Go back. So this is a system of glands working together, releasing many different types of hormones. And I have no idea what the emergent process, actually, the emergent thing that occurs is this regulation of metabolism and this like homeostasis of the body. Now, it's not like the adrenal gland itself is responsible for all of the regulation of the body's systems. It's all of these things working together, and the environment and the need for these hormones and the stresses that are put on the body. Now, the reason that hormones are released is because of stress on the body. Now, that stress could be physical stress, emotional stress. It could be stress related to pregnancy. It could be stress related to breakdown of muscles because of intense resistance training workouts. It could be stresses related to school and homework. It could be religious. It could be family. It could be COVID. It could be all sorts of different things. But hormones are released when the body is in stress. there are many different types. We'll go over a number of them. And hormones will not be accepted in some instances. Yeah, hormones will not be accepted onto tissues unless there are receptors for those hormones on those tissues. If the receptors are damaged, if the receptors are desensitized towards those hormones, like sometimes happens with type 2 diabetes, then you might need more of the hormone, or the gland that's releasing the hormone might need to work harder to make enough hormone to be effective. So we'll talk about what's called the endocrine glands. And what the glands do is they are going to help regulate metabolism. So they're going to help make the body better able to either store fuel or use fuel, depending upon the intensity of the exercise, how much fuel you have. Hormones are also going to be important in the retention of fluid and electrolytes, and also the regulation of calorie intake. So really what hormones are doing is they're like the thermostat of the body, making it so that the body remains kind of level. And what happens is a lot of times one hormone is a regulatory, has a regulatory effect on another hormone. So let's say like this is a seesaw, and this is hormone A, and over here is hormone B, right? A lot of times if there's too much of hormone A, or like if hormone A goes down, then hormone B goes up. And then the more of hormone B there gets, the more that's going to start to trigger the increase in hormone A. And then if there's too much of hormone A, it increases the processing and the synthesization of hormone B. So they act as these regulating mechanisms to control each other. So really the endocrine system is this way that the body communicates. It allows the tissues in the body and the brain to communicate to each other. Now, one way of communicating is through the nervous system. That was chapter 3. And that was through electricity. And we all know that electricity travels very quickly. So the nervous system is a way to communicate, or is a way that the body uses to communicate if the information processing needs to be very quick. It wouldn't make sense for the brain to send an action potential via a chemical communication, because again, that chemical signal needs to take time to dissipate through the bloodstream. So if the action potentials were all based on hormones, it would take a long time for that hormone to diffuse, it's not diffuse, it's to dissolve into the entire bloodstream. And then and only then would you be able to make an action potential. So action potentials and movement are based on much faster means of communication. And again, look at system. And what electricity does, or what chemicals do, and for that matter, you know, I said last class that the eye is like a camera. The eye really isn't. In my opinion, the eye isn't like a camera. All right, the eye does this. All right, and if you think about this, this is point A, like we said before, and this is point B. And if you're going to make a system out of point A and point B by connecting them, then the cool thing about that is that you're going to get those emergent properties, and you're going to get those, like now point A and point B have changed from points and now they're aligned. What's the fastest thing in the galaxy to make this line? right? The fastest moving particle in the galaxy is light. So what your eyes do is they're not a camera taking pictures and stuff. All they are is the receptor for the photons, which create this line between my eyes or between me, which is here, and any other thing in the environment. Could be a table, a chair, a person, anything. And what photons and why your eyes use photons is because they're the fastest thing to draw this line and make a system between you and something else. So as soon as you're a baby and you get like, you leave your mother's womb and you're leaving an environment of pitch black, and you open your eyes for the first time and make that connection with, I don't know what it is. It's a gurney, a light in the birthing room, or your mother's smile or face, right? And then if, let's say, and now your body communicates the same kind of way, but if it can't communicate with photons, it communicates with the next fastest thing, which is electricity. And the next, and another way, but all of these things, electricity, chemicals, photons, they're all just other ways of connecting things. And when you connect the nerves to the muscles, then you get stimulation, and the stimulation is a contraction. So the contraction is the emergent property. It's not, the contraction isn't coming from the brain, it's coming from the system. Now, one of the cool things that you could think about with systems, right, is, I don't know, maybe length is really simple to think about. Maybe it doesn't really like make you excited to think about systems, but my brother is a helicopter pilot. And if I take like this circle here, and I take this line, and I take this little X here, and I take this little line, and then I take a big, huge X, and I take this thing here, and I take this thing here, and this thing here, it doesn't really amount to anything. All of these little parts really don't mean anything. The fuselage of the helicopter doesn't fly. I'll throw this off the bridge and it'll splash in the water. The little X on the back of the plane, the little tail wing, that's not going to fly. But if I put them all together, then what you do is you create just this thing that has aerodynamics. Where does aerodynamics come from? Like, it doesn't come from this part. It doesn't come from this part or the X in the back. It doesn't come from the thing that you land on, nor does it come from the big rotor in the top. It comes from the system itself and the person functioning here, which is a system. And then what emerges from this system, I have no idea how, is flight. That to me is what set me off on this systems theory. Flight doesn't come from this propeller or that propeller or the gears in the rotor or the guy here. It comes from the setup of the whole thing. Now, the reason why systems theory is theoretical is because I have absolutely no idea how that happened and can't explain how, when you create systems, it allows for these emergent properties, but they happen. So what are the emergent properties of these? It's not communication, because again, communication, like information and programming, requires that there's some speech here that's being transmitted, right? It means there's a speech that's transmitted between the nerves and the muscle if there's a communication going on. But if there's just an emergent property without communication at all, and like, it's not like this the rotor says, hey, back propeller, want to communicate about having aerodynamics today? It's 8 o'clock in the morning and we have our first flight. There's no communication going on. Flight emerges without the need of communication because the system is set up that way. That's the beautiful thing. So flight here isn't organized or housed in like this little brain of the helicopter back here. There's no need for the brain of the helicopter because flight emerges out of the setup of the system. So again, there's no need for their endocrine system to have a brain of the endocrine system. And the brain itself doesn't need to control the endocrine system and the nervous system, because the system created by the electricity or the photons or the chemicals, the system created by them, by that itself has emergent properties, and the emergent properties are this homeostasis. So the hormones don't cause homeostasis. This says maintains homeostasis via hormones. It's a causal thing. Hormones are maintained because of, homeostasis is maintained because of hormones. And it says chemicals that control. It's not that control, it's chemicals that are involved in the control and regulation, or chemicals that act with the tissues and the stresses when the regulation of cellular and organ activity is needed. And it does act on target cells, but only if there's receptors and only if the cells need those hormones. So it's like the system of things that is going on that is helping all of this happen. And that's why it says all of these catchphrase systems. Now, the hormones are released into the bloodstream and they need to diffuse, so it takes much longer. So things like movements and activities, things that need to occur almost like without time, are all nerve and electricity driven, but things that are going to last more like chronically over a long period of time are going to be more controlled by your hormones and your endocrine system. Again, if anybody has any questions, please interrupt and let me know. So your endocrine system is like a thermostat where it's monitoring your temperature, your heart rate, your blood pressure. And if there needs to be slight adjustments to these things, then hormones are released. Now, things that hormones are controlling are your substrate metabolism, so food breakdown, and also, especially that this class is going to discuss, or this chapter discusses, is specifically substrate metabolism and fluid and electrolyte balance. Now, substrate metabolism. Substrates are carbohydrate, protein, and fat. So what you eat is going to affect or impact your endocrine system. And that's what we were talking about with sugars. So these are your endocrine glands. Your pancreas here, whoops. Your pancreas releases insulin. And what insulin does is it processes sugars. So this is your pancreas. It's next to your stomach. All right. Alex Trebek died of pancreatic cancer. So what your pancreas does is it releases insulin. When you eat sugar, the sugar needs to be processed. And insulin attaches to the sugar molecules and brings the sugar molecules to the muscles. If the muscles are exercising, then the sugar will be used. But if the body is not exercising, the sugar is going to be delivered to the liver, switched to adipose fat, which itself is an endocrine gland. And that adipose fat will be used as fuel storage for later. Pancreas is a gland, an endocrine gland that is affected by nutrition. So you could imagine if I tax or if I stress this pancreas too much, eventually, just like anything else, if I drive my car too fast without giving it oil changes and no rest, eventually it's going to break down. And that's what type 2 diabetes is. And that's not necessarily all that type 2 diabetes is, right? If I have a lot of sugar in my bloodstream, but I actually have very little muscle mass, then there's no place for the sugar to go either. So if that's the case, it could be resting, it could be just muscle mass, right? It could be the case that I'm completely lethargic and I don't exercise. In that case, there's no place for the sugar to go. So it's not only the case that if I exercise, then I'll be able to utilize the sugars, but the amount of sugar that you eat has a big impact on some of the glands. And it's not just the amount of sugar, because like we said, there's different kinds of sugars. There's sugars that cause a huge spike in the release of insulin that reduces over a long period of time, which are called high glycemic sugars. And then there are other types of sugars that release into the bloodstream over a long period of time. And so these types of sugars, the low glycemic index sugars, are not going to be as damaging to the pancreas as things like just eating straight table sugar, 1,000 calories of Twinkies every day. You know what I mean? Those calories are going to just get into the bloodstream immediately. The pancreas is going to have to work so hard. There's going to be so much insulin in the bloodstream all at once that the receptors to the insulin are going to start to become desensitized. Like if you drink more beer and more beer, eventually you're going to need more and more and more and more and more, right? Same thing with drugs. If you do, you're going to need more and more. So eventually the body needs more and more and more and more insulin to be able to deal with the sugar. And eventually the pancreas just can't keep up with the demand, or it just starts to deteriorate. In any event, there are many things that are stressing these particular glands. Could be exercise, it could be social stress, it could be physical stress, it could be emotional stress, it could be all sorts of different things. These are the glands, and they're all working together. They're making a system. So, I mean, not only do you have 2 points making a system, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 potentially different glands working together. So what is the emergent property of these 10 systems working together and also interacting with the tissues that they're interacting with and also with the nerves? I mean, the emergent properties of these systems that are being created has to be pretty astounding. And I don't even know what they are. Now, there are different types of hormones. There are steroid hormones. You've heard of steroids before. Now, an interesting thing about steroid hormones is that they can diffuse directly into your membranes of your cells because they are dissolvable in fats. These steroid hormones you've heard of before: testosterone, estrogen, cortisol. Now, one interesting thing about testosterone is when you do intense resistance training exercise, and that starts to break down the muscle fibers. And what that means is you actually have actin and myosin. So here's your actin and your myosin in the middle. What happens with intense exercise is it actually breaks these things. So it will actually look like it's been ripped apart. Like the actual myosin and actin are torn apart because of exercise. Like if you looked at a muscle cell under a microscope after a heavy bout of resistance training, it looks like it's been absolutely destroyed, like a hurricane or a tornado went over the slide and it ripped all of the Z discs, it ripped all of this stuff apart. Now, when that happens, obviously the muscle sends a signal to the brain, and that releases, or that's going to result in a release of testosterone into the bloodstream. The testosterone, and we'll show you in a couple of slides, the testosterone is going to go directly to the muscle fiber, And there's nothing to stop the testosterone going through the cell membrane. So the testosterone gets directly into the cell membrane and it causes these mutations, just like the X-Men. So what mutations are caused by the destruction of the muscle fibers because of exercise? Well, instead of, metal things coming out of your hands, the mutation in this case is the regeneration of actin and myosin so that your muscles heal. And not only do they regenerate, but they regenerate with more actin and myosin. So you have even better potential to make contractions. So steroid hormones diffuse directly through the membranes, and they don't need what's called a secondary hormone. A secondary hormone is needed for nonsteroidal hormones. It's kind of like a secondary receptor. They can't cross membranes, so they need to be pulled into the cell by a secondary, like a secondary hormone. There are protein and peptide hormones. A lot of times these are released from the pancreas, the hypothalamus. And there are also amino acid derived hormones like triiodothyronine. These are released from the thyroid. Whereas the release of your nervous system electrical signals is very quick and happens kind of like at one burst, the secretion of hormones is more pulsatile. It happens like a burst of hormone secretion, and then another burst, and then another burst, and another burst. So the concentration of your hormones in your blood plasma at any particular time fluctuate. And they can be pretty dramatic fluctuations throughout either one day or throughout the week. And again, what is going to trigger these hormone bursts is some type of stress, some type of negative feedback. All right. And for the most part, the hormones are going to cause changes in the body that are going to either result in the better utilization of fuel or the increase in tissue production. So just like a home thermostat, we talked about it before. Like the thermostat, if the temperature is dropping and it drops past a particular level, then the thermostat will kick on and increase the temperature. It'll increase the temperature. And then once the temperature increases past a particular amount, that'll click a trigger that will shut off the thermostat, which will make the temperature start to drop. But then when the temperature drops past a particular level, there's an increase in the temperature. So when there's a drop in one hormone and that hormone drops past a particular level, it clicks in the increased secretion of another hormone that gets to a particular level. And when that gets to a particular, so that's how these secretions are controlled by this negative feedback. Negative feedback meaning when one hormone level gets more negative and more negative and more negative and more negative, it clicks the secretion of another hormone that gets more positive that now starts to decrease. So this is what a negative feedback loop refers to. Now, because the pulsatile release of hormones, the amount of hormone in your blood plasma at any particular time is not a great indicator of the activity of the hormone. The other thing is hormones all work with receptors. Some need more than one receptor, but these receptors can become either damaged, so there's a reduced number of these receptors, or they can become desensitized. Now, they become desensitized when either they become damaged or when they're exposed to a huge amount of the hormone that they're receptive to, like when these receptors are exposed to huge amounts of insulin, eventually they just need more and more insulin. So now the endocrine gland that is releasing said hormone needs to work even harder to make it so that the hormone can be effective. Now, there is possibility for the increased number of receptors. It's one of the things that exercise does. It potentially increases the number of receptors for insulin along the muscle fiber. So there is potential for the increase and decrease of receptor sites for hormones to be accepted at the tissues that they're trying to impact. And each hormone has a specific receptor. So if there's no receptor on that particular surface of whatever tissue the hormone is like, so the hormones are in the bloodstream is traveling through the body. So not all hormones are going to affect every organ or every tissue. If the tissue doesn't have a receptor, there's not going to be an effect. So it's like a lock and key mechanism. They call it the hormone receptor complex. That's kind of cool. It's another word for a system here. And what comes from this hormone connected to a receptor system, what emerges from that is the regulation of all of these activities. So it's not that the hormone itself is responsible for this regulation. It's only after binding, only after making a system with its receptor. And look at how many opportunities to make connections each cell has. So what are the emergent properties of these systems being created over and over and over? I mean, and it's not like these systems are simple, like one line and another line, or one dot and another dot. These systems have 2,000 to 10,000 nodes in them. So what is the emergent property of a system that has 2,000 working parts to it? I don't know. It's probably as astounding as the regulation of your body's, homeostasis. Now, where the regulation of the body's homeostasis comes from, I don't know. It's so hard to think of. But for me, to think of it as an emergent property makes it easier for me to understand. So some hormones are steroidal hormones, and like we said, they're lipid soluble. So the hormone can go directly into the nucleus. This hormone receptor system goes directly into the nucleus, and it binds with the DNA. It makes another system with the DNA, and what emerges is this mutation, which is protein synthesis. And protein synthesis is another word for saying more actin and myosin. So this is the cell membrane here. The hormone is going to directly enter the cell membrane because it's a lipid soluble testosterone hormone. The steroid can get directly into the cell. It connects to its receptor, and the receptor is going to either be in the cytoplasm or in the cell nucleus itself. Then the hormone and receptor complex will travel directly through the cytoplasm and into the nucleus. And when it gets into the nucleus, it's going to attach to the DNA and the RNA. And what that's going to do is it's going to result in this mutation. And the mutation is going to allow for protein synthesis. But that's only in the case of a steroidal hormone because if it's a non-steroidal hormone, there's going to be a secondary receptor here.
Once inside the cell, a steroid hormone binds to its specific receptor in the cytoplasm or in the nucleus. The hormone receptor complex activates the cell's DNA, which forms mRNA. This process is direct gene activation. The mRNA then leaves the nucleus and enters the cytoplasm, where it directs protein synthesis.
Smart guy right there. Oh, darn it. I wish I didn't shut that off. But a non-steroidal hormone, because it's not soluble in fats and cellular membranes are made of lipids, which is why you don't want to eliminate fat from your diet, because that will start to break down cellular integrity. A non-steroidal hormone is going to need to have a receptor, a secondary messenger. And that's going to attach to the hormone at the receptor site and carry the hormone into the cell. And these are a bunch of different types of secondary messengers. So it'll be something like, now the steroid cannot pass through the cell membrane here. So there's this other hormone that this particular hormone needs to attach to. It's going to make a hormone receptor complex, which is going to usher the hormone into the cell and allow for changes to occur. I bet this guy can say it much better than I can.
Because nonsteroid hormones cannot cross the cell membrane, they bind with specific receptors on the cell membrane. This hormone receptor complex activates adenylate cyclase within the cell membrane and catalyzes the formation of a second messenger, in this case, cyclic adenosine monophosphate, or CAMP. The cyclic AMP activates protein kinases, or enzymes, that lead to cellular changes and hormonal effects.
Now, I think a lot of this information here is, I don't think it's fair to ask you during exams. I'm not going to ask you this particular process here. It's too complicated. And I think that there are people who get degrees and doctorates in the endocrine system. So for me to expect that you're going to be able to understand each of these kinases and each of these steps is, I don't think, effective. All right. But to be able to understand, maybe it's interesting to you. Maybe it pushes you to learn more about it in, graduate school or whatever. But I think that as long as you're understanding the general concepts of what's going on here between, and the general differences between steroidal and non-steroidal hormones, I think that'll be good enough. There are other types of hormones. They're kind of like a third class of hormones. We don't really talk too much about them. And what they do is they don't go through the entire body. They act kind of at local sites within the body. So they help reduce, they help with inflammation, help reduce injury, pain, and things like that. But we don't go into too much of those types of hormones. We do start talking about the glands and their specific hormones. For instance, the glands that we'll talk about that regulate metabolism or that help make it so that you can burn fuel better while you're exercising are the anterior pituitary, the thyroid, the adrenal gland, and the pancreas. Now, we talked about how important the pancreas is in regulating carbohydrate breakdown. And these other glands are also working as a system to regulate metabolism, specifically carbohydrate and fat during exercise. Now, if you have longer bouts of exercise, like you're running a marathon, then the hormones are going to make it so that the carbohydrate is used later on in the bout of exercise. So some of these hormones are going to switch to the use of fat through lipolysis as opposed to glycolysis, so that you can have carbohydrate or fuel for later in the bout of exercise. So depending upon the intensity of the exercise, certain hormones will be released and be able to switch between carbohydrate, fat. And now, like if you're absolutely in a starved state and you need to start to break down protein into amino acids and such, then other hormones will allow for that to happen. And not only that, but their hormones are going to be involved in the storage of fuel. So not just the breakdown of fuel, but the storage of fuel as well.
There's a greater incidence of ACL, anterior cruciate ligament tears, in females than males. And so obviously people have turned to the question of, do sex hormones cause the difference? And yes, estrogen is the key sex hormone that is involved in that. And the second one is called relaxin, an old hormone discovered in 1924. And they initially found that its role was to loosen or make lax the cartilage that binds the pelvic girdle bones to facilitate parturition. And that function still works in all the joints, in tendons, in ligaments, in shoulder joint, and so on, and causes laxity. So why does it cause laxity? It's because it stimulates an enzyme called collagenase, which basically reorganizes collagen in such a way that it's more flexible, more loose. And unfortunately, in female athletes, it causes tears.
Debbie Downer. So now the chapter starts to talk about the specific glands itself. This is the anterior pituitary. Anterior means the front. So there's 3 different parts of the pituitary gland. There's the anterior, the intermediate, and the posterior. Now, the pituitary gland is attached to the hypothalamus. Remember, the hypothalamus also is innervated by nerves. So there are 3 lobes of the anterior pituitary gland. Sorry, of the pituitary gland, and we're specifically going to talk about the anterior gland here. And the pituitary gland is, now it says it secretes hormones in response to the hypothalamic hormone factors. So there's another system here between the pituitary gland and the hypothalamus. And exercise is causing these stresses. It's breaking down your muscles. And remember, one of the principles of exercise is overreaching. And what that means is that if you want to get stronger, you have to work at an intensity that is higher than what you're normally able to do. And what that does is it breaks down muscles. It causes a micro damage to the muscles, which is going to result in a secretion of all of these glands in the anterior pituitary. Specifically, growth hormone. So exercise is going to cause the muscles to break down. And what happens is the muscles are like, oh man, are we going to become injured? It's like if you have an engineer walking past a bridge and he sees that the bridge is starting to kind of, concrete is starting to fall. I mean, they should have done that in the condo in Florida, right? If they notice or the muscles are starting to become broken down, then they need to be built back up. So when the micro damage happens, there's a release of growth hormone. But if the intensity of the exercise isn't high enough to break down the muscle fibers, then there's not going to be that release in growth hormone. So the stresses on the muscles itself need to be enough to break this down. And then once that breaks down, there needs to be healing, or there needs to be a build up of muscle so that you can perform activities of daily living. And that's when the growth hormone is going to release. It's anabolic, right? And anabolic is the opposite of catabolic. So anabolic is going to result in the increased synthesis of protein. So increase in actin and myosin specifically is what's going to happen. And that's in response to the micro damage of muscle. So this is how muscles grow, right? Hyper is a lot of growth. Muscles do not grow by eating a lot of chicken or having 12 egg whites or hard-boiled eggs a day. It's not how muscles grow. Muscles don't get bigger if you eat a lot of shakes that have protein powder in them. That's not how muscles grow. In fact, the more eggs you eat, the more you're just going to waste them because you don't store the protein like you store carbohydrate. Muscles grow by breaking them, destroying them. And then there's a release of hormones. But if the intensity of the exercise isn't high enough and there is no muscle breakdown, then this process isn't going to work. So it's a result, and the hypertrophy or the release of this is dependent now upon the intensity of the workout that you provide to your athletes. So you have to have the right materials. In the gym, we only have up to 35-pound dumbbells. So it's hard for me to really break down these muscles and result in hypertrophy for my athletes. All right, now when you're exercising, you're using carbohydrate, and it could be the case that at some point you're going to run out of carbohydrate and your body's like, oh man, I don't want to run out of carbohydrate, so we're going to have to start to think about processing some fat so that we can have fuel for later. So the more intense the exercise is, or the longer the duration of the exercise, the more this is going to kick in. So your anterior pituitary gland is secreting growth hormone in response to stresses, in response to exercise. So that's the first hormone that the chapter mentions. Your thyroid gland is in your throat. All right, maybe I can go here and just give you a reminder where. So this is your thalamus. Your pituitary gland is in the middle of your brain. Your thyroid here is in your throat here. It's right behind your hyoid bone. And your thyroid gland is going to release triiodothyronine and thyroxine. And these are going to be distributed to all of your tissues through the bloodstream. And it's going to result in the increased burning of fuel, the increased processing of food. So I'm going to write an equation here that you might want to think about. Resting metabolic rate. And instead of resting metabolic rate, you could also think about it as basal metabolic rate. So just the basal metabolic rate. And we talked about that a little bit earlier. These refer to the very least amount of energy, the lowest amount of energy that we all need in order to function. And just to remind you, this does not mean resting metabolic rate divided by basal metabolic, and that should be an R. That's just one or the other. Now, in any event, the amount of food or the amount of energy that your body is spending every day, it can be estimated using this equation, 500 plus parentheses 22 times your fat-free mass. So the weight of your muscle. And let's just go through that real quick, all right? Now, I'm about 20% body fat. And I'm about 65 kilograms. So 65. Man, I wish I had my phone. 1 second, let me get my phone so I can do my math. I should be able to do that in my head, but I'm not a math professor now, am I? So let's go real quick and do this math so I'm not wrong. There's nothing worse than being wrong at math in a lecture. So I'm 65 kilograms and multiply that by 20%. So that means that I'm about 13 kilograms of fat. So now 65 minus 13, I can do that. That's 52. So that means I'm 52 kilograms of fat-free mass. And 52 kilograms times 22, 52 times 22 is equal to 1,144. Let's go 1,140 is fine. And then add 500 to that is 1,640. So that's the way to estimate the basal metabolic rate for somebody who is 65 kilograms and 20% body fat. Now, what it means, though, is that the metabolic rate, the amount that my body burns fuel, is dependent upon fat-free mass, is dependent upon the amount of muscle that I have, because muscle burns fuel and fat doesn't burn fuel. So that means that if I start lifting and I build up the amount of muscle mass that I have, I'm going to burn more energy just by living. And if you exercise and you increase the amount of muscle mass, and that increases, and that exercise is resulting in a natural increase in the metabolic rate because of the secretion of hormones, then this now becomes the new way to regulate body mass and body weight. Weight management is now built on fat-free mass. It's not based on running on a treadmill. That's the old way of thinking about it. But the new way of thinking about weight management is increasing muscle mass, because if you increase muscle mass, you naturally increase your resting metabolic rate. You're naturally increasing the amount of calories that you're burning each day. That's going to help make it so that you can more easily manage weight. Not only does triiodothyronine and thyroxine increase the metabolic rate so that you have more fuel during exercise, but it's also going to lead to an increase, again, just like growth hormone, to an increase in protein synthesis, which is actin and myosin. It's going to result in an increase in not only the number, which is the frequency and the size of the mitochondria, but what that's going to do is make it so that you can utilize. Remember, mitochondria is where sugars are connected to oxygen and made into more ATP. So if there's more ATP, because there's more mitochondria, there's more energy, that's going to stimulate more exercise, which is going to stimulate more glucose uptake by the muscle cells to utilize as fuel, which is going to result in less fat storage. It's going to increase the burning of sugars. Glycogen is what you store sugar in your muscle and your liver. So it's going to, and glyco is the lysis of glycogen. So this is going to be the transformation of glycogen that's stored in your muscle and your liver back into glucose. It's also going to result in gluconeogenesis, right? Remember, and I have to plug my computer in a second. So gluco is sugar, neo is the new creation of, and gluconeogenesis is coming from, is in the new creation of sugars are coming from broken down proteins and amino acids that are just floating through the bloodstream. So really what these two hormones are doing is making it so that you have fuel, and now if you don't have enough carbohydrate, it's going to start to break down free fatty acids and move those towards the mitochondria so that you can use the the fatty acids for fuel. So all of this stuff is designed to make it so that you have more muscle, more fuel, so that you can perform activities that you need to more effectively. Does anybody have any other questions about this stuff? Now, the thyroid gland and your anterior pituitary gland, they're connected, obviously, and they make another system. So not only do you have like the thyroid gland itself is a gland, but that gland is also working as a system with other glands through other hormones. So this thyrotropin is another gland that allows for communication between the thyroid and the pituitary. It travels to the thyroid and stimulates T3 and T4. Doesn't that imply that there's another system here, and what emerges from that is these particular activities here, or these particular functions. That's not to say T3 and T4 increase these things here, or that the thyrotropin is the thing that's responsible for this, but these things are all emergent properties of the exercise that you're doing in the first place. Now remember, if there is no exercise, none of this stuff happens. And if you're exercising on a planet that doesn't have gravity, that's not causing stresses on the tissues, none of this happens. Right? So all of this stuff is based on the fact that you're functioning in an environment that is causing some type of stresses. And now what we're starting to talk about is the adrenal medulla, the adrenaline, the adrenal glands, where adrenaline is going to start to be released. And again, here, fight or flight. Again, hormones being released to make it so that you can either have more fuel or have a better reaction so that you can perform physical activities more effectively. There are two different catecholamines that are released in the adrenal medulla, and the medulla is the outer layer, the inner layer of the adrenal gland. And I'll show you one more time. The adrenal gland is here. It's right above your kidneys. So these are your adrenal glands here. So when my guys are doing their warm-up, what I'm trying to do is manipulate their adrenal glands. So if I can get their adrenal glands to release, let's see where I'm at. Sorry, I'm just gonna find them. Here we go. So if I can increase the release of epinephrine and norepinephrine from the adrenal glands and get that into the bloodstream. And what triggers that is exercise. The exercise is going to increase the need for, remember, sympathetic nervous system is the one that increases my vasodilation. It distributes blood from my stomach and intestines to my muscles. It increases the utilization of carbohydrate for fuel. This is the one that makes everything go up, sympathetic up, parasympathetic down. So if I have them do exercise, it's going to trigger the sympathetic nervous system, and it's going to release epinephrine and norepinephrine into their bloodstream. But remember, the norepinephrine and epinephrine isn't going to travel throughout their blood instantaneously. It's going to take time to diffuse, not diffuse, dissolve. And if that's the case, I want to make sure that I give that time to happen so that all of these catecholamines, the epinephrine and norepinephrine, have an opportunity to get to all of the tissues, which is why you want to do a 5 to 7 minute warm up. And that 5 to 7 minutes will allow for the release of epinephrine and the time for those catecholamines to be distributed to the tissues that they're trying to impact. And like I said, these catecholamines are going to increase heart rate. So it's going to deliver more blood and oxygen to the muscles. It's going to allow for an increase in contractile force. It's also going to allow for glycogen to be broken down along with fats. And that's preparing for the reduction in carbohydrate during exercise. So as the carbohydrate levels start to drop, there's an increase in the need to create more sugars. And so all of these things are very good for gymnastics. I want to increase contractile force. I want to increase heart rate. So a good warm-up to me is warming up not only the heart and the butt, but it's really trying to release hormones. My guys don't quite understand. So I have them do like run in place, but instead of like running in place with a particular intensity, sometimes it looks kind of like they shuffle in place. And my I guess concern is that there's not enough intensity of exercise to impact the sympathetic nervous system, and then they won't get the emergent properties of increased heart rate, better utilization of carbohydrates so that they have more energy during practice. You obviously want more blood flow to skeletal muscle, increase muscle temperature, increase the malleability of the muscle. So I'm specifically trying to manipulate hormonal release during a good warm-up. If you have any questions, please feel free to interrupt. Now, the adrenal cortex, which is the outer layer of the adrenal gland, releases corticosteroids. The main corticosteroid is cortisol. And what cortisol does is it breaks down protein catabolism, the breakdown of protein into amino acids. So this is here going to start to become the concentration of cortisol is going to increase when you don't have much carbohydrate. So it's triggered when there's a need for gluconeogenesis, and gluconeogenesis is gluco is sugar, new sugars generated. And new sugars are generated by the breakdown of free fatty acids. And now there's like remnants of free fatty acids floating through the bloodstream, along with now the beginnings of protein breakdown. And now these remnants can all be recycled because remember, they're all just carbon, hydrogens, and oxygens. So they're all ripped apart and reorganized into new sugars. But this is going to happen when your concentration of muscle glycogen and blood glucose and sugars to use are reduced. And this is going to be during bouts of long endurance type exercise without proper sugar or blood glucose maintaining procedures. Like, for instance, I have my guys drink Gatorade, during exercise. So if you are exercising and you don't have the fuels in regards to sugars, then these things are going to now come into play in terms of fuel production, and cortisol is going to be released. Pancreas releases insulin. And what insulin does is it lowers the amount of sugar in your bloodstream. If there's no insulin, or if the body is desensitized to insulin, and I eat 1,000 calories of sugar, the sugar is just going to sit in my blood vessels, especially if I'm not using my muscles or I don't have fat-free mass. And what it's going to do is it's going to bring the sugars out of the blood. So the glucose levels in the blood reduces. And where is it bringing it? It's bringing it into the muscle cells. And it's going to use that fuel for physical activity. When your muscle cells have too much sugar in it, the insulin attaches to the sugars, brings it to the liver, and it switches the sugars to glycogen. And it stores the glycogen in the muscle and in the liver. And it also increases the potential for adipose fat. Glucagon works opposite of insulin. And what that's going to do is it's going to work when you have situations where you don't have enough carbohydrate or sugars in your diet. And what that's going to do is it's going to start to break up the glycogen, which is stored in the muscles and in your liver, and try to make sugars out of the glycogen, or it's going to try to make sugars out of remnants of fat and protein. So glucagon is going to be released when you're in a situation where you just don't have enough carbohydrate in your diet. So I don't understand when people have a low carb diet, especially when they're exercising. Right? Because glucose must be available to tissues. And if glucose isn't available to tissues, it's going to make glucose out of something. Now, one way that I try to regulate the metabolism so my athletes have enough glucose so they can have enough energy is by just having them drink Gatorade as opposed to water. And one of the reasons why is, I think we talk about it later on, there's a couple of reasons to drink while you're exercising. One is to replace fluids that are lost through sweating. Another is to replace electrolytes that are lost through sweating. And another one is to replace fuel. Well, if you're exercising in an environment that you're not sweating too much, or my athletes are indoors, it's never too hot because we have an air conditioner, and they're never doing activity for more than like 30 seconds at a time. So for the most part, my athletes aren't sweating too much. They're not losing a lot of fluid, nor are they losing a lot of electrolytes. So for me, the most important thing that I want my athletes to do when they're drinking something during workout is to replace glucose stores. So they don't drink a lot, but I'll have them like have a sip of Gatorade, every 30 minutes or so, like the amount of a Dixie cup. And that helps them maintain their glucose levels so that they don't start to have to spend their muscle glycogen. Now, if you burn all your muscle glycogen, that takes a lot longer to like restock in your muscles. And then this is why, like, if the guys are working out and they don't have enough sugars, they start to burn muscle glycogen. The next 2, 3, 4 days in the gym, they're dead, absolutely dead, because it takes time to regenerate the muscle glycogen. So they want to be eating carbohydrates so that they can use the glucose for the fuel, and they can kind of maintain the glycogen, muscle glycogen, as a stockpile. But if they don't have enough carbohydrate in their diet and they're continuously beating up this, it's like when you're using your glycogen stores, it's like you're doing the overdraft. Yeah, you can get money out, but like it's going to cost you $30 every time you do it. Right? So you want to keep the money in the bank so that you don't have to go into your savings account. And then by the time you're starting to use this, you're literally using your muscle mass for fuel. So we want to try to potentially avoid that. So to me, you want to have, again, the percentages, and we'll talk about this later, is about 50% carbohydrate, 30% fat, and 20% protein. And again, remember, 20% protein, you would be, wow, why do we need less protein than fat? Remember, you don't store protein. And fat is very important for cellular structure, cellular integrity. So you don't want to get rid of fat, but glucose must be available. So I don't understand diets that don't have a good amount of carbohydrate. Now, for somebody who's not exercising, understood. We got to consider dropping this down for people who don't exercise. And that's at least 50% of the country, but we're talking about exercise physiology in this course. So now, in order to have enough sugar during exercise, you're going to have some interaction between your liver, because your body doesn't store enough glucose in the bloodstream. So there's going to have to be some type of release of liver glucose. So there's going to have to be some glycogenolysis occurring, especially if your exercise intensity or duration is long enough. And glucagon, epinephrine, norepinephrine, cortisol are all responsible for increasing the circulation of glucose, this is the slide that made me understand that I want my athletes to do a good long 5 to 7 minute warm up to allow for the release of these catecholamines so that I can increase circulating sugars and fuel to my bodies. So really, it used to be the case that we did a warm up so that we could stretch and do splits and stuff like that. And more, I don't believe in that kind of warm up. I believe in more of like a hormonal warm up where I'm trying to release these things so that I can increase heart rate, increase contractile properties, increase the utilization of carbohydrate. And once that happens, then what I'll do is I'll give them another 5 minutes of doing like their open stretch or whatever. But that's only so that I can placate to their psychology because they think they need it, but I don't think they do. All right, where are we at here? How much more? So as the exercise intensity increases, there's a greater release in all of these hormones. So a lot of the increase in hypertrophy, in strength, in power is based on this exercise intensity as opposed to me, diet. And if I don't get the exercise intensity right, then I waste a lot of time in the gym. I think of exercise intensity as like a recipe. If I want to make chocolate chip cookies, right, I have a particular recipe. And if I make the chocolate chip cookies with the right recipe, then what happens is really good chocolate chip cookies. But if I just change one thing about the recipe, and it says that it's supposed to be like cooked at 325, and I just put the oven, whatever, I don't like 325, I like 250 better. You know, you're just not going to get the right result. And you can change any part of the recipe. You can change any part of the exercise recipe, and you're not going to get things right, because a lot of it is based on the stresses that you put on the system. If the stresses aren't high enough, there's not going to be the release of these hormones. There's not going to be the increased synthesis level of actinomycin. So again, duration and intensity of the exercise are really critical. Let's see what we got here. All right, so you'll notice here that, let's go clear here, clear all the drawings. So as exercise time, so the person is exercising for longer and longer and longer and longer, you'll notice that the level of glucose in the blood doesn't change very much at all. But in order to maintain that homeostasis of glucose, you see there's an incredible response to all of these particular hormones, and they're all at different times, different rates or speed or velocity of release into the bloodstream. Some of them are released very quickly and dissipate. Some of them are released continuously in almost like a linear manner throughout the entire bout of exercise. And this is here increasing almost linearly to continue the increase of glycogenolysis, gluconeogenesis, the breakdown of remnants, so they can be transferred back into glucose quick enough so that the blood glucose levels during exercise can be maintained. But these are all working as a system. This is a system. And what's happening as they work together and what's emerging from the system of these hormones interacting at the tissues is the maintenance or the homeostasis of this blood glucose level, which is a pretty astounding emergent property. And none of these things have brains. Epinephrine doesn't have a brain. Cortisol doesn't have a brain. They're all working together, though, so that this thing can emerge. It's like the same thing you watch on a television. Like this is like saying this is the tube part. This is the plug. This is the stand. This is the LEDs. None of those are making the television actually function. Like if I take just even one wire out of the television, it won't work. Or if I take the plug off of the television, it won't work. But the screen and the program and what I'm watching isn't housed in any one part. And there's no brain of the television that's controlling all of these parts. And the parts of the television don't have a brain. So this mechanism here, this maintenance of this thing is emerging from things that don't have a brain. That's amazing. That means you don't need necessarily to have a brain for organization, for structural organization. Like slime molds don't have brains, and they can organize. So all of this is still pushing towards maybe there's a regulation mechanism here that's happening that's creating an unbelievably consistent, result in one of the most important fuels for exercise, arguably the only and the most important substrate for your brain and for your muscles, and they're all being regulated by hormones. Glucose is not a hormone. Glucose is a substrate. The rest of the hormones are working together to kind of like maintain this. That is an emergent property of the endocrine system working together. And it's not just one hormone doing it, it's all of them working together. All right, so one of the things that happens is if you look at exercise, let's take a look at this. If you look at the duration of exercise, as exercise time increases, the person is exercising longer and longer and longer and longer. All right, you would think that they would start to burn more and more glucose, right? So glucose is released and then glucose is burned, but there's like almost at some point as you exercise, there's a leveling off of glucose. But if you look at insulin concentrations during exercise, it actually continues to decrease. But if you need to utilize more and more glucose, you would think that maybe the insulin levels would be maintained or they would increase a little bit so that they can process more glucose as the bout of exercise continues on. But the reason that this happens is because imagine if the pancreas needed to keep working harder and harder and harder and harder and harder, eventually the pancreas would fail. So what happens, although there's a reduction in the insulin released from the pancreas, there's actually, I think it'll say this, there's actually an increase in the sensitivity of the cell to insulin. So remember we said that insulin needs, and some of these hormones need to have receptors. Well, when I exercise, the plasma concentrations of insulin can decrease because the sensitivity or the receptors, some of the receptors remain dormant when you're not doing bigger bouts of exercise. And as the exercise intensity increases, more and more of the receptors are made available for insulin, for the sugars to, and for any insulin that's in the bloodstream to attach to. So it allows for more glucose to be pulled into the cells without continually taxing the pancreas more and more and more. So although there is and should be a relatively level amount of glucose in the bloodstream after you start to get into, now, why is it so low here? Well, remember, your body isn't using glucose at this particular moment of exercise. It's 0 seconds, so you use an ATP. But then as the bout of exercise increases, there's a release of glucose glycogenolysis into the blood so that you can have glucose for longer bouts of endurance activity. But your pancreas and the work of your pancreas can reduce because there's an increased sensitivity of the muscle cells towards insulin during exercise. If you're doing longer bouts of exercise, endurance exercise, the mobilization, the movement of free fatty acids and the breakdown of fat for fuel becomes more and more important, especially as the muscle glycogen, especially as like that bank, there's no more glucose in the blood, muscle glycogen is being depleted. The body does not want to use protein for fuel. So the body is going to start to break down fat as its substrate. And as a person gets better and better at exercising, or they become a more fit endurance trainer, this is actually going to happen sooner and sooner because the body doesn't want to get to a point where glycogen is depleted. So it'll switch triglycerides. Remember, a triglyceride is 3, which is the three fatty acids attached to a glycerine backbone. And these fatty acids are going to be broken down, transported to the muscle. They're going to go through its beta oxidation and be shuttled into the mitochondria so that you can use the fat for fuel. And this whole process, this whole utilization of fat for fuel is stimulated by decreased insulin. And there's going to be a decreased insulin when there is either there's just not enough blood glucose, not enough carbohydrate in the body at the time. So it's going to start to release cortisol, and the cortisol is going to start to allow for the breakdown of proteins. So all of this is going to be stimulated by the fact that you just don't have enough carbohydrate in your diet.
So hormones sometimes are exciting things to study. And in 2012, a discovery of a hormone called irisin has gotten a lot of people excited because it turned out that exercise in mice led to secretion of irisin through several steps. The first step is that it increased a release of a gene coactivator called PGC1 alpha, and PGC1 alpha transcribed a gene, FNDC5, and the protein product of that gene then cleaved off a piece which started circulating in the blood as irisin. Now, the exciting part of that is that the irisin in mice converted white fat, which made them obese, into beige fat, halfway to brown fat, which is an organ filled with fat, but that doesn't store the fat, but it uses it to produce energy. It basically burns fat. And so this opened this gate and expectation that we can use that hormone to combat obesity, metabolic disease, diabetes, all kinds of afflictions, part of metabolic syndrome that are associated with obesity. So this is obviously only 2 years into discovery. There have been 100 papers already published on that hormone. And clearly much more research needs to be done because there's some controversy whether it works in humans and whether the conditions of exercise were not right. But in mice, it certainly made a fascinating story and very exciting opportunities for research.
So the field of endocrinology is obviously expanding, and it gives us all opportunities to potentially study things. You know, when I graduated, I thought that my life was limited to being a personal trainer at Workout World. And I realized that I didn't need to do only that. To me, I can be part of the exercise and health sciences field by being a professor, by being a teacher, by being an endocrinologist, by being a nutritionist, by being an exercise planner, by doing research. So the fields, all of these fields are continuously expanding, which is another reason why I can't expect that you'll know everything. You can only just be exposed to what it is that you're, exposed to, and do the best with what you have. All right. Another role of hormones during exercise is to regulate fluid. When you exercise, your plasma volume decreases. And what that does is it makes your blood more viscous. It makes your blood thicker, more like oil, because there's less fluid in it. And when your blood plasma volume decreases, it increases the need for your heart to pump harder. You lose water. And when you lose water and your blood becomes thicker, it increases the strain on your heart. Your heart just has to squeeze the blood out harder. And it takes a lot more for, your little teeny blood vessels are very small. Imagine forcing some viscous material through these teeny blood vessels. Because of that, there's more peripheral, or there's more restriction of the blood flow at the very smaller, at the smaller venules and teeny capillaries and such. So during exercise, the reduced plasma volume increases potential heart strain. So hormones, specifically in now not the anterior pituitary, but the posterior pituitary gland, the adrenal gland and the kidneys, help to maintain fluid balance. The posterior pituitary secretes antidiuretic hormone and oxytocin. Now, these are produced in the hypothalamus. So the hypothalamus is one of the structures that we talked about in the brain that has to do with the secretion of, with the release of electrical signals. And so the hypothalamus and the pituitary are connected. And this is another example of a connection between the endocrine system and the neurological system. So the neuroendocrine system resulting in even more emergent properties. And what antidiuretic hormone is going to do is it's going to increase the absorption of water at the kidneys, and it's going to try to hold on to water. It's going to make it so that you waste less water. So if it's really hot, if it's a situation where you're not pulling in enough water, then rather than having the water wasted from sweat and wasted in the urine, the kidneys are going to absorb the water so that it can use the water for tissue and cellular maintenance and energy production. And the release for the antidiuretic hormone is, again, based on the volume of water that's in the blood plasma. So as you exercise and you're losing more water, and the water, and the blood becomes thicker and thicker and becomes more viscous, all right, the concentration of blood the concentration of hemoglobin in the blood increases. That's going to stimulate the release of antidiuretic hormone. What that's going to do is it's going to make it so that you're not peeing out or sweating as much water, and that water goes back into the plasma volume. All right, and this is only happening, again, with severe dehydration. So if you can maintain hydration status, you can avoid that. Aldosterone is released by your adrenal cortex, and that has to do with the retention of salt by your kidneys. And remember, salt makes you thirsty, so the retention of salt in the kidneys is also going to result in an increase in water retention, so that you don't change the osmolarity of the tissues of the kidneys. All right, and your kidneys also act as they're an organ, but they can also act as an endocrine gland. They're considered an endocrine gland because they do factor into the regulation of fluids in the body. Let's see how much more we need to go with this stuff. Let's see. All right, so the most important thing about the water retention is really when you need to be considerate of the replacement of fluid and electrolytes, and that's going to be have a lot to do with like atmospheric conditions. So if you're working out in an environment that's very dry, that you're not losing a huge amount of fluid and electrolytes, then you might want to switch your fluid intake. So fluids are introduced for one of three reasons. We just said number one is to replace lost water. Number two is to replace lost salt, sodium. And number three is to replace fuel or carbohydrate. So if you're working out in an environment that's going to promote a lot of water loss and sweating, then you got to focus on this goal of your fluid intake, which is going to be more to rehydrate and replace electrolytes. So if you're doing endurance running in a very humid environment where sweating doesn't really, doesn't happen effectively, and you're losing a lot of water because you can't regulate your body temperature, then water, sodium, Gatorade, water is the best is the best fluid. The other thing is the more complex you make this fluid, the more difficult it is for you to digest the fluid. So it takes a lot longer to get into your plasma concentration. So if you are concerned with hydration status because you're doing endurance running in the heat, then the best thing to drink is just straight up water, because it's the fastest thing to break down in the stomach and then to get the fluid into the bloodstream. But for my athletes that are really not sweating too much, they're not losing a lot of electrolytes, the most important thing with this fluid retention is that I'm providing a particular option that allows them to replace fuels so that they don't have this reduction in glucose levels, so that they don't have the increase in cortisol and the burning of fuels aside from carbohydrate. Let's see what else we got. All right, and we talked a little bit about before how hormones can also regulate calorie intake. Calorie intake is food, like eating, and calorie intake is a behavior. So now not only are hormones changing electrolytes and the retention of sodium and osmolarity and all of that, but they're now starting to potentially impact a behavior. All right, calorie intake is eating, and your hypothalamus is the appetite control center. So when you eat and the carbohydrate gets into your bloodstream and that attaches to insulin, the insulin is going to travel through the entire body's vascular system, and eventually that insulin is going to get to the brain. And the hypothalamus is responsible for the feelings of being full or not being full. And the information is, in some instances, sent by your stomach or your gastrointestinal tract. So when you eat food, what happens is there's a stretching of the stomach. And that releases a particular hormone that goes to your brain, and it tells your brain that you're not as hungry as you used to be. So this gastrointestinal tract stretching is going to potentially reduce caloric intake. Now, one of the things is that you can shut this off so that you don't get this suppressed appetite. And the way that some companies do that is by using high fructose corn syrup as opposed to glucose. If you look at Gatorade has straight glucose in it, but Powerade has high fructose corn syrup. And what high fructose corn syrup does is it doesn't suppress appetite. So like you could go to McDonald's and you can eat, a 3,000 calorie Big Mac, and you could also drink a huge Coca-Cola that has high fructose corn syrup, and the Coca-Cola won't make you full. But if the Coca-Cola had glucose in it, it would potentially make you more full, so you wouldn't be able to eat the product. So you can even manipulate these hormones, or the hormones that are triggering hunger signals. And that's what is happening when you're eating sugar. When you're eating large amounts of sugar, this ghrelin, which increases appetite, is stimulated. And that increases appetite. So you eat sugar, you eat food, that food results in a release of hormones that travels through your brain. And when some of those hormones get to your brain, it tells you to increase your appetite, or it results in an increased appetite. So this is the reason here why I have a hard time eating candy corn. This is the reason why even Lay's, potato chips, their whole thing is, I bet you can't eat just one. Yeah, right, because you can't. You're eating carbohydrate that is increasing the result, or, you know, especially if you're eating, if you're, you know, drinking Coca-Cola and so there are ways that companies can change the constituents of the food, the things that make up the food, so that you can manipulate caloric intake.